friends, welcome back to Beyond Pipelines. This is Pipeline 107 and I am going to talk about pipeline flanges in this lecture. Pipeline flanges were covered under my earlier lecture, Pipeline 103 Part 2. So I recommend you to watch that lecture to continue with this Pipeline 107. In this lecture, we will try to understand the following key aspects about pipeline flanges, various flange standards, flange rating and rated pressure, correlation of rated pressure with material grade, correlation of rated pressure with design temperature. It is also called temperature derating, pipeline system design pressure versus full rated pressure, and correct selection of a pipeline flange. All these 6 key concepts are very important for every pipeline engineer or even a piping engineer to understand to perform the optimum design of pipeline system and the correct selection of flanges. So let's start with flange standards first. The most commonly used flange standards in oil and gas industry or petrochemical industry are ASME B16.5, ASME B16.47, MSSSP 44 and ASTM A694. ASME B16.5 covers pressure temperature ratings, materials, dimensions, tolerances, markings and testing of pipeline flanges and flange fittings. This is the most commonly used pipeline flange standard in the industry. I have covered mainly the American standards here, which are very commonly used in the oil and gas industry. However, there could be other countrywide regional standards also being followed, which can also be referred, but the concepts shall remain same. There are ISO standards, there are some other Norwegian standards, but the concept should be same. And I have covered here mainly the American standards, which are widely used. So this ASME B16.5 is considered as the most important standard because it provides the pressure temperature ratings, which is very widely used for piping industry mainly, and pipeline has to, whenever there is interface of pipeline flange with the piping flange, then it becomes very important for the pipeline engineer as well. These covers the rating class designations of 150, 300, 400, 600, 900, 1500 and 2500 in sizes half inch to 24 inch. I tried to find out the logic behind using these numbers 150, 300, 400, 600, but could not really find out any specific logic. Only one hint I can give you that from 300 to 1500, 2500 class, when I divided these numbers, say for example, when 300 was divided by the pressure rating of 300 class for A105 flange, which is 51.1 bar. When I divided 300 with 51.1 bar, I got the number of 5.87, and then I tried to correlate that, and it applies to everywhere. For 600 class, if you divide by 5.87 or 5.88, you will get its rated pressure in bar gauge. Likewise up to 2500. But this logic didn't work for 150 class. Anyway, this is not like a used or well-known kind of a logic. I just tried to find out some correlation which is vaguely explained here, but you don't have to not necessarily follow it. Yeah. So this SMEP 16.5 covers flanges and flange fittings made from cast or forged material and also plate material for blind flanges. As you can understand, blind flanges are just the flat uh, plates or blanks, so they can be used from plate material. They can be manufactured from plate material. This standard also covers the requirements and recommendations regarding flange bolting, flange gaskets, and flange joints. So when we say flange design or flange joint, obviously it is not just the dimensions of the flanges but also the bolting and the type of gasket, the gasket factor, the torquing values, and all of these come in the picture. Therefore, flange standard ASME 16.5 or other standards are not just limited to the flange material and its dimensions, but also correlated with flange bolting, the bolt material selections, the gaskets, gasket factors, and overall flange joints. So this is very important aspect to be remembered. Let's see what are these various standards other than 16.5. So 16.5, as I said, is the most key standard where the flange pressure rating classes are defined, and every other standard cross refers to this. Okay, so this becomes one of the central standard for pipeline flanges or even the piping flanges. So 16.5 provides the sizes from half inch to 24 inch. What about the larger sizes? Because some of the pipelines or pipings can have larger diameter than 24 inch. So ASME B16.47 is used for larger sizes. It has got two types of flanges, type A and type B. The pressure temperature ratings of type A are same as ASME B16.5, whereas type B has lower pressure ratings, and this type is used for less critical service applications like water. For oil and gas industry, type A flange is normally used. Now what about ASTM A694 and MSSSP 44 standard? So we should be curious to know when these two standards are used, when we already have 16.5 and 16.47. So I'm going to explain this, and this actually results into the difference between piping flange and a pipeline flange. So we will unfold the story now. So let us see the aspects covered by A694 and MSSP 44 standards. Okay, so they cover the sizes from 12 inch to 60 inch. Okay, so not just limited to 24 inch, but they cover up to 60 inch. Okay, the pressure temperature ratings covered in these two standards are 150 to 900 class. It doesn't cover higher ratings. Normally, we don't see larger diameter flanges with pressure ratings or a very high pressure large diameter pipelines, because most often it will become uneconomical way from the capital investment point of view. The pressure temperature ratings and drilling templates are matching with 16.5 and MSSP 44 flanges, so they are compatible to make the interface joint. So suppose piping industry is using 16.5 or MSSP 44 flange template, drilling template, and you have to connect pipeline flange made with MSSP 44 or A694 with the piping flange, then the drilling templates are always going to match. So the drilling templates of all these four standards are always matching with respect to the pressure temperature rating classes. Similar to MSSP 44, A694 is also used for carbon and alloy steel forgings and pipe flanges, fittings, valves, etc., where the the high pressure transmission service with high strength transmission service pipe are used. I will, in the next few slides we'll understand what is high strength pipe and high strength flange materials. So we saw that NC ASME B 16.5 is mainly covering, and 16.47 is mainly covering the normal material grades, okay, which are used in the piping industry. But for pipeline industry, we select high strength material. The main idea of selecting high strength material or higher SMYS, the normal piping SMYS is, let's say, 35,000, 30 to 36,000 psi. Whereas for pipeline industry, for cross country pipelines, we always select higher grade materials like 42,000, 52,000, 60,000, 65,000, all the way up to 70,000 psi material strength. The higher the strength of the pipe selected, material selected for the pipeline, the lower will be the thickness of it. So when you are talking about, say, hundreds of kilometers of pipelines, then with the lower thickness, the overall cost will become economical. So to optimize the pipeline thickness and the cost, capital investment, always high grade materials are used for pipelines. Another thing is pipelines are normally buried or well supported along the length, and it doesn't have very complex geometry like what we see typically in the plant piping, where the supports are very difficult to provide and the configurations are very complex in the plant. So for piping, normally normal strength materials are used, whereas for pipeline, the advantage of it can use the higher strength materials and thereby reducing the thickness and overall economics of the pipeline systems. So with respect to the higher grade pipes, okay, which are available as per API file, the flanges also shall match with these high grades SMYs or yield strength. So the MSSP 44 and A694 standards provide that option of higher grade flange materials. So if you have a API file X52 pipe which has got a SMYs of 52,000, so which we call it as API file X52, then you can select the MSSP 44 F52 or ASTM A694 F52 flange, which will have again the 52,000 psi SMYs. So the weld end thickness of the flange will match with the pipe thickness or pipeline thickness, so that welding becomes feasible and convenient, and the weld end thickness of the flange satisfies the hoop thickness criteria, hoop strength criteria. So these are the two important aspects which are covered by which that flexibility is provided by these standards, because they cover the high grade flange materials. Now let us see flange ratings and rated pressures for basic understanding, not just for pipeline industry but also for piping and the the static engineers. And then at the end of this lecture we will cover the aspects of pipeline flange selection and the criticality about its weld end thickness. Okay, but let's see flange rating and rated pressure now. The pressure temperature ratings given in ASME B 16.5 are maximum allowable working pressures in bar gauge at temperature in degree centigrade for the applicable material and rating class. There are various materials that can be used for making the flanges as well as the pipe. For example, let's say carbon steel pipes, let's say alloy pipes, let's say stainless steel pipes, let's say duplex stainless steel pipes, cast iron pipes. So all these kind of a variety of materials are available for pipes and flanges. Okay, so ASME B 16.5 has tried to standardize all these materials into various material groups so that their design can be standardized, and based on the strength of these materials for various groups, they have given the pressure temperature ratings, or the the pressures that can be that these dimensions or these flanges can withstand. So these are called pressure temperature ratings. So let's take the sample of the typically used piping flange material, which is ASTM A105, which is a standard grade material, not a pipeline high grade material, but this has got a around 35,000 psi yield strength, and this material is covered under material group 1.1. And let us see uh, what are the different rated pressures at ambient temperature or 38 degrees centigrade for ASTM A105 across all the pressure classes. So this table will explain that to you. The 150 class flange rating class will have a design pressure of 19.6. 300 class will have 51.1. 400 will have 68.1. 600 will have 102.1. 900 will have 153.2. 1500 will have 255.3. And 2500 class will have 425.11. So what is the meaning of this? So this means the standard flange design and the bolting template given in ASMEB 16.5 can be used for material group which covers ASTM A105. Okay, and that standard template, standard flange dimensions can withstand these pressures, allowable pressures in bar gauge for these various pressure classes. And for each of these pressure class or rating class, flange rating class, there are different flange dimensions or bolting templates given in ASMEB 16.5. So like for example, for 150 class 10-inch flange, it can withstand 19.6 bar gauge. It will have certain diameter of the flange OD, certain diameter of the bolt circle diameter. Number of bolts will be defined, the bolt hole will be defined, and that template can be, that template, if somebody wants to use or manufacture the flange and use it, then with those dimensions and those specific material grades and bolt grades and gasket material, the flange joint can withstand 19.6 bar pressure, uh, and it will be called as flange rating of 150 class. So this kind of a standardization provides a very good commercial aspect across the industry worldwide, so that if you are ordering a valve from say X country, okay, let's say Italy, and that valve will be supplied by Italian manufacturer to say, let's say Malaysia, and the flanges for the various piping and pipeline components are being manufactured say in India, Indian manufacturer, and they are being exported to Malaysia, where the plant and the pipeline system is being installed. And let's say some vessels are coming from South Korea, some of the other elements are coming from America, some items are coming from, or equipment are coming from Japan, some compressors are coming from let's say Germany, and all of these are to be connected by means of flanges together, flange joints together. And if all of them are using these standard templates as per the required pressure rating classes, then there is a guarantee that all of them will match. The bolts will be matching, they can be torqued together, the flange joints can be connected together, and they will withstand, all of it connected together will withstand the rated pressure given in ASMEB 16.5. So that is the magic of standardization done by ASMEB 16.5, and that is why it is called the most one of the most critical and important standards used in the oil and gas and petrochemical industry in the globe. I hope you have understood the importance of flange rating and rated pressures. You need to explore 16.5 for various templates given, bolting templates given, and various the rated based on each flange rating classes to understand what I am explaining here. Let's move to the correlation of flange rated pressure with material. As I said before, we just saw the pressure rating, the rated pressures of ASTM A105 material. So since 16.5 standard has standardized the bolting templates or flange dimensions for various rating classes, depending upon the strength of each material, its rated pressure will vary. So they have standardized the dimensions. So now if the strength of some material is higher, it can withstand higher pressure. If the strength of the material is lower, it can withstand lower pressure for the same flange dimensions. So that is the beauty of doing such standardization, and that's why there are various groups covered here in the standard, like carbon steel group, stainless steel group, duplex stainless steel group. So all these material groups, with respect to its strength, tensile and yield strength, they are covered together, or they are like grouped together. And now let us see what happens when you compare the allowable pressures in bar gauge for all the rating classes, but for two different group materials. Okay, so for comparison and for explaining to you all, I have considered here two groups. One is 1.1 group and another one is 2.3 group. These groups are given in ASME B16.5. Group 1.1 typically used material is carbon steel A105 flange, and group 2.3 typically used material is stainless steel A182 316L grade material. So these are very commonly used materials, and these two are very commonly used groups. So if you see, the carbon steel has much higher tensile and yield strength as compared to stainless steel. Even though stainless steel has got some anti-corrosive properties as compared to carbon steel, but the strength point of view, carbon steel is higher than stainless steel. So if you see, for the same templates, drilling templates or bolting templates of the flanges and dimensions of the flanges given in 16.5 for various pressure rating classes, being CS carbon steel A105 being higher strength material, it can withstand higher allowable pressure or higher design pressure. So if you see, for 150 class, carbon steel flange can withstand 19.6 bar gauge, whereas stainless steel flange can withstand 15.9 bar gauge. So it is almost, I can say, 3.5 to 4 bar gauge lower. Okay. Let's take another example of 900 class. For carbon steel A105, it can withstand 153.2 bar gauge, whereas stainless steel flange can withstand only 124.1 bar gauge. So one important aspect to be remembered by all the piping and pipeline design engineers is that, suppose you are trying to connect in your system, you have carbon steel pipeline with carbon steel flange, or piping for that matter, carbon steel piping which has got the flange welded to the pipe as A105 flange, and however the valve is made from, say, stainless steel A182 material. Okay, it is a solid valve. So suppose you want to connect the valve with this carbon steel flange, stainless steel valve with carbon steel flange. Obviously, suppose it is 900 class stainless steel valve to be connected with 900 class carbon steel piping flange. Obviously, because the bolting templates are same, the dimensions of the bolt holes and bolts and the outside diameter of the flange, all these key parameters, key dimensions are going to match. But one must remember that stainless steel flange, though it is matching with the dimensions of carbon steel flange, it can withstand, its rated pressure is only 124.1 bar and not 153.2 bar. So when such selection is there, such combination is to be selected, then your overall system, the design pressure of the system becomes the lowest, which is the governing one. So even though you are talking about 900 class and you have got carbon steel piping and flanges, because you are using stainless steel valves or some other stainless steel elements, flange elements, the overall rated pressure of the system has to be selected based on the lowest of these two groups, and therefore 900 class, such a system, piping combination of carbon steel and stainless steel system, the rated pressure of this system is going to be 124.1 bar gauge and not 153.2 bar gauge. So one must remember this. Okay. So friends, let's see correlation of flange rated pressure with temperature. This is also known as temperature derating. One can easily understand when we say temperature derating. So as the temperature goes up for any element, its strength reduces. I have already explained in multiple lectures before. So same thing is going to happen with the flanges. The flange rated pressure gets reduced at higher temperature. When a flange joint or a pipeline or piping system faces higher operating temperature, its rated pressure capacity gets lower. So to understand this, how much is the derating impact? I've given here the summary of material group 1.1, which is very commonly used CS flange grade A105. I have compared across all the rating classes with various temperature rising from 38 degrees centigrade to 200 degrees centigrade. You can see that the allowable pressures are gradually reducing as the temperature goes up. Let's take an example of 600 class at between minus 29 to 38 degrees centigrade, which we normally call it as the ambient temperature range. It's 102.1 as the rated pressure in bar gauge. That goes down at 100 degrees centigrade to 93.2, at 200 degrees centigrade to 87.6. So this is purely the result of material strength getting reduced with the increase in temperature. Very straightforward concept, and I believe one can easily understand this. But this summary table makes it very easy to understand how much is the impact of temperature on rated pressures. So when selecting your design pressure, you also have to consider the design temperature. So if your system has, say, 100 degrees centigrade as a design temperature, then your pressure, the 600 class can withstand is only 93.2. So suppose your one good example is, suppose your requirement is 100 bar gauge pressure, okay, design pressure requirement, and your temperature is 100 degrees centigrade, then it will not fit under 600 rating class, flange rating class. You have to consider 900 rating class, because at 100 degrees centigrade, the 600 pressure class will give you allowable pressure of only 93.2, whereas your system design pressure requirement is 100 bar gauge instead of 93.2. Therefore, you have to go for one higher flange rating, and you have to select the 900 class rated flanges in your oil and gas system that you are designing. Whereas if your design pressure is same 100 bar and your design temperature is, let's say, 50 degrees centigrade, then your allowable pressure is 100.2 bar gauge, and therefore for 100 bar gauge design pressure requirement of your system, you can select 600 class flanges. So this is how the important it is. Yeah, so you should be careful about the temperature aspect while selecting the pressure class and allowable pressure or rated pressure. Now let's see pipeline system design pressure. Okay, pipelines are normally very long in distance. Some cross-country pipelines are hundreds of kilometers long, and as I explained before, for the high strength material selection for specifically for pipeline, the simple logic is to optimize the thickness of the pipeline and then save the capital investment. Yeah. Similarly, if you have a system design requirement, system design pressure requirement, like for example, you have a pressure source. Let's say there is a reservoir from where your oil and gas hydrocarbons are coming out, and when it reaches to the surface, from the subsurface to surface, at the surface level, considering static head, if your source pressure, highest pressure at the surface is, let's say, 80 bar gauge, okay, then if you try to consider, and temperature is, let's assume, 50 degrees centigrade, okay, then your system requirement, flange rating point of view, if you select 80 bar gauge 50 degrees centigrade, it will be considered under 600 class, flange pressure rating of 600 class, and 600 class can actually allow you up to say 100 bar at 50 degrees centigrade, okay. But since your source pressure cannot go beyond 80 bar gauge, okay, there is no point in designing your pipe thickness, flange thickness, pipeline flange thickness and pipeline thickness to go to be designed for 100 bar gauge, even though full rated flange rated condition is 100 bar gauge. So you can design your pipeline thickness for 80 bar gauge, which is your source pressure, and there is a guarantee that source pressure is not going to go beyond that. So this 20 bar gauge less design pressure can be selected as your pipeline system design pressure, and thereby equivalent thickness reduction is possible, and that much will be your capital investment saving. You don't have to spend extra cost for the thickness of your pipeline to be 100 bar gauge. Instead of that, it can be 80 bar gauge. So therefore, pipeline systems are always designed based on the actual source design conditions, or sometimes the safeguarded design conditions, okay, to make them optimum, in terms of the design criteria. So they are optimized and then the cost is reduced. Whereas the on-plot piping, because there are so many sizes, so many elements, so many items are involved, therefore the contingency requirements, inventory requirements and all these material maintenance replacement requirements are may vary from various sizes to various dimensions and all that, and therefore for on-plot piping, normally standard full rated pressure classes based design is done. So your on-plot will, in most cases, it will be fully rated to flange rated conditions. However, your connected pipeline system will still be designed for the source based maximum design pressure requirement, okay, tailor made, you can say, okay, to optimize the cost. So this is what is explained in this kind of slides. So we have studied that flange rated pressures so far in this lecture. Yeah, based on pressure class, it has fixed rated pressure values. For example, class 600 has got a full rated condition of 102 bar gauge at 38 degrees centigrade and 100.2 at 50 degrees centigrade. However, if the pressure source of a pipeline system, let's say centrifugal pump, or the example which I gave you was the reservoir, it has got the maximum pressure of 80 bar gauge, okay, then in that case you don't have to unnecessarily design your pipeline system for full rated condition of 102.1 bar gauge. Instead, the system can be designed for 80 bar gauge, because above that the pressure cannot go, because your centrifugal pump has max discharge pressure of 80 bar gauge. Yeah, However, the flange connections like flange valves, flange fittings, flange joints, etc. will be automatically suitable for full rated condition of 600 class, which are 102.1 bar gauge, because we have just seen in the previous slides that the flange ratings are globally standardized to certain dimensions and certain rating tables. So those will be automatically designed for its rated condition. Yeah. But pipeline wall thickness optimization is possible by reducing the the design pressure to the actual source pressure. Okay, in this case almost 20 bar gauge, 21 bar gauge of saving is possible by, as compared to considering the full rated capacity of class 600. Hope you have understood this concept very well, and it is very important for every pipeline engineer to optimize their pipeline design. So the same thing is explained here now with the kind of a schematic picture. See this pipeline which is connecting from one central gathering station to crude oil processing plant. I have already explained the in the types of pipelines and flow lines in my earlier lecture in this series. So what are the remote gathering stations, what are the wells, flow lines, trunk lines, and central gathering stations to the lines, pipelines or bulk lines carrying the fluid from central gathering stations to the main processing plants and exports pipelines. So I have taken one example of this pipeline is transporting the liquid from central gathering station to the oil processing plant, and it has got that central gathering station which gathers the liquid from various remote manifolds and wells and all that is gathered there, and then there will be a centrifugal pump located there to transport it at 80 bar gauge to central processing plant. So this 80 bar gauge is the max the pump pressure can go. The flange rating will be 600 class, and its rated pressure will be 102.1 bar gauge at 38 degrees centigrade and 100 at 50 degrees centigrade. However, since our pressure source itself is limited to 80 bar gauge, there is no need to consider to calculate the pipeline thickness for 102 bar gauge, 102.1 or full rated condition. We can safely consider the thickness of pipeline suitable for 80 bar gauge. And if we are talking about very long pipeline, let's assume that this pipeline is 50 kilometer long, then that 20 bar gauge equivalent thickness will be saved. So this is a huge capex saving, cost capital investment saving, which can be realized, in by wisely selecting the design pressures. And therefore pipeline system design pressure selection is very important, and it has got a lot of economical advantages. So one must remember that. Now last but not the least is pipeline flange design and selection. Many times people get carried away, or engineers get carried away by selecting the flange only on the basis of the bolting template, with respect to the rating class. So if two rating classes are matching and bolting templates are matching, they consider that the flange is safely selected. But that's not the case, because the bolting templates are same across every material group. Okay, but if you are selecting lower grade for the flange material, and your bolting class is going to match with the adjacent pipeline flange which is having, say, high grade material, so bolting templates will match, but still the thickness of the flange for the lower grade material will not match, because the lower the grade or strength of that flange material, its hoop strength, or hoop thickness is going to be higher. So it will require higher thickness at the weld end, and if your pipeline is designed with high grade material, then its hoop thickness is going to be lower, and in such case your high hoop thickness of the flange grade uh, cannot be welded, with the pipeline pipe of lower grade, of higher strength and lower hoop thickness. Okay, it will become a mismatching joint, and tapering of lower grade flange material also will not be allowed, because it will reduce its strength. So one must remember that pipeline flange is not selected just based on the rating classes and matching the bolt templates, but you have to also be careful about the grade of the flange material and its hoop thickness based weld end thickness, and that should match with the pipeline, and therefore it becomes important that your flange material grade, flange strength, ideally shall match with the connecting pipeline material strength. So if your pipeline, say the pipe is selected for API file grade X65, then ideally your flange material also shall be MSSP 44 F65 or A694 F65, so that your hoop thickness of the pipe and the weld end of the flange will match. So so be careful about this. Yeah. So let's see in detail about this configuration what I've shown in this picture below. Yeah. So the flange design is defined based on two parameters: flange dimensions, which is bolting templates, and weld end thickness. Flange dimensions are specified in 16.5 or 16.47 or MSSP 47, MSSP 44 for various pressure classes. Okay, these are the standard bolting templates. Whereas weld end thickness, okay, has to be specifically calculated based on the material strength for the applicable design pressure. And it has to match with the connected pipeline thickness to satisfy the weld configurations given in pipeline design codes B31.8 and 31.4. Okay, so the key of matching the weld end thickness with pipeline is to select the same grade for flange and line pipe. So X42 pipe with F42 flange and X65 pipe with F65 flange. So one must remember this. Yeah. So in the picture I have given here, the flange dimensions are flange OD, bolt circle diameter, number of bolts, bolt diameter, and flange thickness. Okay. Whereas the flange weld end thickness is basically dependent on flange material, its strength, which is SMYs, pipe material, which is pipe strength, allowable weld configuration as per 31.8 figure I5 or 31.4 434.8.6.2. Okay, so one should not just select the flange on the basis of flange dimensions or bolting templates, but they should be very, very careful and cautious in considering the flange weld end thickness and the grade of the flange and corresponding to the pipeline grade. So be careful about this. So the key parameters to remember. So wrap up the flange pipeline flange design and selection. I have just covered summarized these basic points which one must remember. So the key parameters, so left hand side is set by the parameters to be considered, and right hand side is set by the selection. Yeah. So pipeline system design pressure, okay, which is in our case 80 bar gauge, and rated condition is 101.2 bar gauge, okay, for 600 class, for example. Flange pressure rating classes. So this our pipeline system which we saw was considered under 600 class, but about, I've already explained 150, 300, 600, 900, etc. Then selected pipeline material strength, which is X42, X52, like that, and selected pipeline thickness. So pipeline thickness will be calculated on the basis of the design pressure of the pipeline system and the material strength selected. Yeah. So this forms the left hand side. Now you have to select the flange based on these key parameters. Okay. So the flange rating class will be selected based on the pipeline system design pressure. So if it is 80 bar, then it will become 600 class. Okay. Flange material strength, as I explained before, it must match with pipeline material strength. If your pipe is X65, then pipeline material shall ideally be F65. okay, so that its weld end thickness in terms of the hoop criteria will be same as the pipeline thickness, and then you can satisfy the welding configurations given in the pipeline code. Welding configurations are very important, and I will try to explain them in later part of my series, where we will talk about the welding configurations, and in case of the localized section replacement, where if you have different grade materials available, then how to understand them and how to select them. Okay, we'll cover that separately. But here important thing is, ideal situation is flange material strength shall match with pipeline material grade or strength, okay, SM wise, and by thereby you can then match the weld end thickness of the flange with the selected pipeline thickness. And this is the most important criteria, which some people by mistake can forget, can neglect, and they will just focus on the bolting template, matching bolting templates based on the pressure rating classes. But no, the welding end thickness of the flange plays very important role, okay, because the overall hoop strength across the weld joint has to be considered. So I believe I have covered nice kind of concepts about pipeline flanges. It also tells you the basic difference between piping and pipeline flanges, and also how the optimization can be done by selecting the lower overall pipeline system design pressure as compared to full rated pipeline rated pressures, and what are the advantages of that. And I have also explained the standards used for pipeline flanges, where the high grade materials are covered. And last but not the least was to explain you about how the pipeline flange has to be designed or selected. So it is not just on the basis of matching bolting templates with the piping flange, but the weld end thickness of it has to match with the connected pipeline grade and thickness to meet the hoop strength as well as the welding configuration given in the pipeline codes. So hope this lecture gives you the clarifies the most important topic in the pipeline, which is pipeline flanges. Okay, thank you so much. Hope you liked it.